Unit 6 is on bonding. So we're going to be doing a lot of drawing of structures and talking about polarity and not polarity, and then talking about shapes. Remember all those shapes that you had to learn? Yay, we're back to all that. Today, though, we're just going to kind of introduce the concept of bonding, and I want to hear what y'all have to say about bonding. So answer some questions here. And I want class participation. First period was dead. I wanted to beat them. Why do you have so many? You really only need one thing to write with.
Color code my pens, like how you color code those.
I see. I'm glad you. No, I'm good. I don't need to try one. Thanks. Appreciate the offer. He's got, for those of you at home, let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, like 23-ish pens on his desk. And then an eraser, and then a correction tape, a calculator, and a bottle of water. It's impressive, Peter.
Thank you.
You're welcome. So what is meant by a chemical bond? What does that mean? It's bonded. Together, okay, sharing. Anything else? Is a bond a stick? A stick that holds two balls together? Is that a bond? No. They're attracted to each other. Did you say yes?
No, I'm saying yes to their no.
Oh, to their no? Yes. I am so confused. You were saying yes to their no? Yes. Okay, I'm done. Miles, no talking for the rest of the period. You can't say anything. So basically, y'all, that's what's your impression when you think of bond? What do you think of? Sharing electrons. I'm okay with that, except ionic bonds, we know, don't share electrons, so it's close. What's holding these things together? You kind of alluded to it. And attraction, charges, okay? Ultimately, how atoms bond has to do with the concept that they're getting together because they're creating a situation where they're going to be in a lower energy state. Nothing happens in this world for free. That's something my dad always used to say when they're like, oh, if you enter this, you can get this for free. I'm like, no, there's always a catch. And there is a catch. The reason these things come together is because you end up getting an overall lower energy of your system. These electrons get, not electrons, sorry. These nuclei are going to get close enough to each other so they don't repel, but they can still advantageously feel attraction of the other atom's electrons. And there's a point where that can happen. So that is a chemical bond. And this is an example of two hydrogen atoms coming together. These little dots, they're not all electrons. What do the dots represent? We've kind of saw that in last unit. What do these dots represent? The space that, where? Right, where you might find an electron. So this is kind of a visual representation of all the different places that one electron in hydrogen might have been at some point in time. Okay, so moving on, we're going to talk about the types of bonds that we might have. The first one is ionic. Ionic bonding, we know, is electrons are transferred. So what is the big difference between two atoms that will participate in an ionic bond? One's negative. How are they negative or positive? What's making them negative or positive? What'd you say? Right, they have one more electron, but what property makes them steal versus share? Again, that is the statement was they want to have a full outer shell. I'm not big on the whole 8 is great, atoms are happy thing, because I don't want you to personify. But again, there's a property. Yes, electronegativity. So if things have really big differences in electronegativity, they're going to steal, one will steal electrons from the other one, right? Remember my whole thing I did with the pen? Y'all remember that? Okay. So if I'm way more electronegative than Irene, I'm going to steal them from her, and I'm going to have her electron. Now I'm negative, she's positive, and we attract through electrostatic attraction, or we bond through electrostatic attraction. If I could spell, it would be great. Now, big on the AP is Coulomb's law, and I'm going to show you Coulomb's law in a little bit. It refers to ionic bonding. Coulomb's law basically is a law that talks about the attraction between oppositely charged things. And so we can also call this a Coulombic attraction. If you see Coulombic attraction on the AP, do not freak out. It is this. It is opposite charges. You can have Coulombic attractions between any two things that are oppositely charged, not just ions. They will sometimes refer to trends using Coulombic attractions. They might say they'll say something like, why is the Coulombic attraction between the nucleus of francium and its valence electrons less than the Coulombic attraction between the nucleus of lithium and its valence electrons? And what would your answer be? No, don't use electronegativity. That's the attraction. Why? This is last unit. Why is the Coulombic attraction between the nucleus and valence electrons of francium less than that of lithium? More shielding, exactly. So it's using the exact same things you already know, just putting in a fancy word that freaks people out. You already know this, so I don't choose to teach a separate thing on Coulombic attraction. It's something that's common sense, opposite things that attract. So ionic bonding is referring to that attraction because of electrons being stolen. Covalent bonding, and this particular publisher, don't know why, they say covalent bonding and polar covalent bonding are two different things. They're calling covalent bonding nonpolar. I'm always going to write the word nonpolar in front of it, so it'll be nonpolar covalent or polar covalent. Nonpolar covalent, electrons are shared equally. So what can you tell me about the difference in the electronegativity of two things in a nonpolar covalent bond? They're the same. Pretty dang close. Because the second they become different, we get a polar covalent situation where they're still sharing. So Irene's going to grab, and she's going to be more electronegative than me, but we're still sharing. She's not stealing them from me. Okay, so that's our polar covalent situation. This results in a charge separation in the bond, partial positives and partial negatives. I'm going to show you guys in a little bit how to draw what we call a dipole moment, and we talk about this in detail tomorrow. But when you see the word partial, the way it is shown symbolically is with a lowercase delta. That's a partial positive. That's a partial negative. We already kind of saw that when we were doing water, right? And we were talking about how water likes to attract to other water molecules through, and those partials mean that we have polar bonds. And I'll show you how to apply that in a minute. So are we good with the different bond types? All right, moving on. Electronegativity then, we've already studied this last unit a little bit, is the ability of an atom and a molecule to attract shared electrons to itself. Okay? So we're talking about things that react, things that form bonds. Ranges of electronegativity are from about 4 for fluorine and 0.7 for cesium. These guys are seriously different, those two. And everything getting close to fluorine is going to have a higher electronegativity. Here's electronegativity table. This is a list of all the different electronegativities. Do y'all want to memorize these? Yes? No, I'm not going to make you memorize them. I'm actually totally against the whole math thing because it's never going to be on the AP where you have to do the subtraction and figure out the difference and then determine the bond type. Do y'all remember that last year, that if it was less than like a 0.4 difference, we said it was nonpolar covalent, that if it was in between like 0.4 to 1.6, it was a polar covalent, and anything greater than 1.6 was ionic? That's not going to be an expectation this year. In case it shows up on your homework, because Miss Rozier and I, she does homework and I'll do tests and that kind of thing. So my understanding that it's not, but in case it shows up, just know that that's about where things lie. And all you would have to do would be, if you're looking at the bond between O and F, you subtract the two. That's 4 minus 3.5. That's a difference of 0.5. So that would be a polar covalent bond. It's really easy to do. But you're not going to be responsible for that on the AP. You are going to have to rank the polarity of bonds, though. And how do we do that? We just look at the distance apart between the actual atoms. If they're really, 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 really far apart, what kind of bond is it? Ionic, because it's a huge difference. So that's why ionic bonds, ionic, are primarily made up of metals and nonmetals, because those are the furthest apart on the table. Nonmetals together will rarely make an ionic bond. This is why I don't like it, because sometimes, in some cases, things that we know that aren't ionic are showing up with a difference of electronegativity 1.6, and you're like, why isn't that an ionic compound? It doesn't always work. So just know the further apart you are, the bigger the difference, the more polar or more ionic you are. So lithium and fluorine react. Which has more attraction for an electron? Fluorine. Why? Very much more electronegative. What can you tell me about this bond type? Why did you say it was ionic? It's perfectly correct. Well, more than that, we don't know. Big difference. It's a metal and a nonmetal. So because it's a metal and a nonmetal, we know it's ionic. Okay? So how they're attracted, I'm going to go a little step further here, is that we have our, it's not fluorine, sodium, it's lithium and fluorine. Lithium gives up its electron and becomes what? Positive, not more positive. It becomes positive because it's ionic. What did fluorine do? It took the electron, so it became negative. Those are literal charges, and now the attraction between the two is going to be electrostatic or Coulombic, and they're going to stick together. Now, not one lithium and one fluorine gets together and that's it. We end up getting something called a lattice, where bunches of lithium ions and bunches of fluorine ions get together. Think about your table salt at home. You know how you have little crystals? Is one of those crystals an Na and a Cl? No. It's a conglomeration of them. It's a lattice work of those ions together. Okay? What about the bond between fluorine and iodine? Which has more attraction? Fluorine. Why? More electronegative. What can you tell me? These are a lot closer together than the other two were, right? So we're going to assume, without doing the math, that we have a covalent bond, okay? But they're big enough in difference that, what type of covalent bond do you think it is? We're going to say it's polar. Tomorrow I'm going to go into detail about how to draw these, but there's something called a dipole moment that you need to be able to draw, which is basically indicating the polarity of each bond through the use of arrows. So you always have an arrow pointing toward the more electronegative atom, because that's where all the electrons are going. So which way are all the electrons going? Toward the fluorine. So you draw an arrow toward fluorine, and then you put a little hatch mark at the end, or hash mark, whatever. All the electrons from all the clouds are kind of unevenly distributed to the left. And tomorrow I'll show you some diagrams of how they really look when you're looking at the big picture of this. And then in addition, in a dipole moment, you have to put your partial charges. So what would be the partial charge on fluorine? Negative. And this partial is a lowercase delta. And this is a partial positive. So when I ask to draw a dipole moment, that's what I mean. You draw the arrows toward the more electronegative atoms. Okay? We'll cover that more tomorrow. So here, it talks about the relationship between bond type and difference in electronegativity. If you have no difference in electronegativity, it's a nonpolar covalent. If there's a little bit of a difference, it's a polar covalent. If there's a huge difference, it's ionic. Now, they use the terms covalent and ionic character. It's exactly as it sounds. The bigger the difference in electronegativity, the more ionic character it has. The smaller the difference in electronegativity, the more covalent character it has. Covalent, the optimum covalent bond being equal sharing. Okay? So don't let those terms scare you either. There's nothing they're going to throw at you that you can't figure out or don't already know something about. It just might be a different word, some word that you haven't heard before. All right, so we're going to make a stab at this and arrange from most to least polar, starting with A. All of them have F in common, correct? So the difference is between the C, the O, and the F. So which one is going to be the closest together on the table? O and F. So these are the closest together. Which is the furthest apart? C and F is farthest or furthest. I don't know which one to use. I'll say further. Further apart. So what can you tell me about their polarities? The O to F is the least polar because they are the closest in electronegativity, making C to F the most polar because, I heard a high five back there, because those are furthest apart. Remember, the further apart they are, the bigger the electronegativity difference. All right, so then NF is in the middle, right? All right, C to F, N to O, and SI to F. We kind of have to jump around here a little bit. C to F, they're about 4 apart. This has S and F in common. So how would you compare the SI? Remember, level takes precedence. Yeah, SI, these guys are further apart. These are closer. So what about N to O then, would you say? I would say they're the closest. So let's rank from, I'll actually rank them correctly. What's the least polar? N to O, and then C to F, and then SI to F. Got it? Y'all are looking at me funny. Okay, I think you get it. All right. Part C, I can tell which one is the least polar without even looking at the table. That's right. There is 0 polarity difference between those two. Which do you think is the next closest together, B to Cl or S to Cl? S to Cl. This one's an easy one. And then B to Cl. Got it? And because I can't stand not writing everything down, I'm going to go ahead and rank this one while we're at it. We good? The ranking is a big deal, okay? This is what you do in lieu of that math to figure out the polarity. This is the kind of thing that they're going to ask. Okay, so now we're going to put polarity out of our head for a bit and just talk about the whole concept of ionic compounds. Ionic compounds we already talked about as being a situation where the electronegativity is so different we form ions. One steals electrons from the other. By definition, one of the definitions of an ionic compound is a compound that conducts an electric current when melted. Why do we have to melt salt to put an electric current through it? I don't want to say it's aqueous because aqueous means water. It's liquefied, right? Which allows for movement. I'm doing a little charade dance up here. No one's getting what this means. Wave, sort of. Yes. Ding, ding. You're good at charades. Flow. We need to be able, these electrons need to be able to freely flow from charge to charge to charge. And in that structural lattice, that can't happen. So we have to melt these. What else? What's another situation where ionic compounds can conduct electricity? When we dissolve them, how? In water. Well, at least the soluble ones. We know there's some ionic compounds that don't dissolve, and if they don't dissolve, remember we talked about electrolytes? Okay, so some majority of salts will actually be electrolytes and conduct electricity in an aqueous solution. Okay. Usually, again, made up of metal and a nonmetal or a metal and a polyatomic ion. If it's got an ion in it, it's ionic. All right, lattice energy. Hugely important. I'll probably usually just write LE for short when I'm doing these. Lattice energy is, by definition, the energy released when 2 ions of an ionic compound come together to form a crystal. Now, I know the whole release thing blows people's minds. They don't get it. But if I were to ask you the reverse, you'd get it. If I said, okay, I'm going to break that lattice. So what do I have to do in terms of energy? Put energy in. Putting energy in is a positive, correct? Right? So if I put energy in to make them come apart, the opposite has to be true. When these ions come together, you're in a lower energy state, so energy is released. Okay, so your typical lattice energies that you see in tables are negative. But don't let the sign, again, throw you off. A negative 500 lattice energy is bigger than a negative 200 lattice energy. On a number line, it's not, but in terms of energy released, 500 kilojoules being released is more than 200 kilojoules, right? The negative just tells you what direction that magnitude is going. All right, so this is Coulomb's law. Dun-da-da. Coulomb's. All the seniors are gone, but I don't even think that's how you spell Coulomb's. How do you spell Columbus? No, but it's not Columbus. It's C-O-U. I think it's C-O-U. Somebody look it up with your iPad. C-O-U-L-O-M-B-S, I think. Is that it? That's L-O-M-B. So Coulomb's law, apostrophe S. All right. Coulomb's law says that lattice energy is equal to the relationship of the attraction between the two ions, which in this case is your charges of your two ions, or whatever. The thing about Coulomb's law, you're going to be doing it in physics. And you guys aren't going to be looking at the attraction between ions. You're going to be looking at the attraction between separate little particles, be them positive and negative electrons, be it a positive car and a negative gazelle, I don't know, whatever you do in physics. But this works for anything, two things that are oppositely charged. So you take the charges of the two ions in this class and you divide it by the radius of the lattice. So let's look at sodium chloride. What would I have for sodium's charge? Positive. And I know in physics they're like, oh, it's not really positive. They're lying. We're not lying. We're establishing that, no, it's not literally a positive charge as in that many coulombs. However, it's a representation relative to other ions. Yeah, the charge of sodium is half the charge of calcium, okay, literally. But we, instead of using all those numbers, just say +1 and +2. So here we have that, and here we have -1 for the chloride. So the higher the charges of the species, what can we say about the lattice energy? The greater the lattice energy. So that's an important thing you need to know. You need to understand lattice energy depends on charge, and it also depends on radius. So what's bigger, sodium or chloride's ion? Chloride. So here we have the chloride ion, and it's negatively charged, right? And here we have a little bitty sodium ion that's positively charged. The radius we're talking about is that radius. That radius, the bigger it gets, the easier that lattice is to break. And that might not seem to make sense, but if you think about taking a stick, say you had a meter stick and you break it, it's easy, right? And you take half of it and you break it again, and then you try to break it again, and doesn't it get harder and harder to break? So the shorter this lever, the closer these two are together, the harder it is to break. And that shows up numerically. The smaller the radius, the higher the lattice energy. So more energy is released when it comes together, and it requires also more energy to break. So what do you have to know the formula? Yeah, you need to. It's not on the AP sheet, and all you need to remember, QQ over R. Lattice energy depends on charge and radius. If you got that down, you're good. You're never going to have to mathematically calculate the lattice energy, but you need to know enough to where you can talk about why one salt has a higher lattice energy than another, and you're going to compare their charges and their radius. So we are not going to calculate the bond type. We'll order them to the best of our ability, and right now I just basically want to see if you can recognize bond type quickly. Sodium chloride. Good. Lithium hydride. Ionic. These two, because it's H, it causes problems. This is why I hate the numbers. But let's pretend both of those are covalent. Of the two, which one would be more polar covalent than the other? HF, right? This would be more polar because it's further away. And remember, level takes precedence. This would be less polar. All right, and then what about RBO? Ionic. So let's see if we could rank these ionics. This won't be, RB is huge, huge. That to me stands out compared to the other two ionic ones. So to me, that one would be, let's think about lattice energy. RB is humongous. So it's a small lattice energy. This is our smallest. Okay, so what would be our most? Let's see if we can fit. And again, this is sketchy. Oh, no. No, really? I would go with the lithium because it's the smallest. The charges are the same, +1, -1. So I would say that the one that's the smallest radius with the most lattice energy is LIH. This is going to have the highest. And again, this is a sketchy way to ask this question. Don't lose sleep over it this way. I do, however, expect you to be able to do this. This is an old AP problem. So it's telling you if you put K and attach it to these 4 different halogen ions, halide ions, that's the trend there for the lattice energy. So what was lattice energy again? QQ over R. Forget the K. I just want to know what we're looking at here. So does charge play a part in this trend? I just spit. From the difference is because of charge. Is that what you're telling me? No. Why? Because it's all plus and minus, right? So the charge has the charge is not involved in the difference. The charge doesn't explain why those numbers decrease. What explains why the numbers decrease? The radius. And what is it saying? The larger the radius, the what? And that works, right? Look at the numbers. It's going big to small. Smaller the lattice energy. Okay? Using that equation is the best way to answer these questions because your equation is your proof. And then up here, number 5, what classes of elements typically unite to form compounds containing ionic bonds? Yes. Good. And then metals and polyatomics, or 2 polyatomics. Give me an example of 2 polyatomics coming together. NH4, not NH3, NH4 ammonium sulfate, ammonium nitrate, ammonium anything. Okay. And that would be it for the day. I know it's a short day. You guys okay with a short lecture? All right. Okay, so go ahead and start on your homework.